Welcome everybody to a new young session within our online seminar series, Machine Learning Needs Mathematical Optimization. We are very happy to come back. And we have today 3 speakers coming from different places. And as usual, we will place the questions to any of these 3 speakers until the end. So our first speaker is Sandra Benítez-Peña, and she's a postdoctoral fellow from Universidad Carlos III de Madrid in Spain. And today Sandra is going to tell us about a clustered approach to data envelopment analysis. The floor is yours, Sandra.
Thank you so much for the introduction, Cristina. Well, as she has said, I am going to talk about a cluster approach to data envelopment analysis, mainly focused to the study of benchmarking. And this is a joint work with Peter Bogtov and Dolores Romero Morales from the Copenhagen Business School. Well, this is the outline of my talk. First, I will tell you about a little introduction of this work. I will tell you why we decide to use the cluster and the feature selection, because we need to perform also feature selection. Then I will move to the modelization of clustering and feature selection. First, I will expose a MLMP formulation. Then I will talk you about some constructive heuristics. Then I will move to local search heuristic, and after all the methodology is explained, I will show you some numerical results in a simulated dataset and also in a real-world dataset. After all, I will conclude with some remarks and some points for future research. So regarding the introduction, what is benchmarking? So in benchmarking, we are given a set of k-frames which use all of them the same A inputs and produce the same outputs. And the performance of the different frames is measured in terms of the output that they produce in relation to the inputs they use. So if they produce a lot of output but consume a few of inputs, it is said that the frame is efficient. Otherwise, the frames will be inefficient. So in benchmarking, the aim is to compare the performance of different frames against others. Which are the different applications here? So we can find benchmarking of electricity distribution system operators. Also, we can find the application in the private or even in the public service. For example, in hospitals, universities, schools, and so on. So one problem that we can find in benchmarking in the different firms that we have is, for example, the heterogeneity. What happened with heterogeneity in this case? We have to answer the questions of, do all the firms, for instance, the hospitals, behave the same? Because we can find, for example, some hospitals that are more focused on hair surgeries or maybe on physical therapy. Otherwise, we can find some hospitals that serve to rural areas, so they have not specialization. They have to know how to treat every disease, whereas maybe there are cities in which we can find so many hospitals, each one with their specialty. So we cannot actually compare the performance of everything against every other. We have to try to find some groups, some clusters. So our proposal here is to develop a novel methodology that finds possible groups of firms that more or less behave the same and have the same properties. And at the same time, we want to find which are the priorities or the characteristics that make those firms to form these groups. And hence, we have to perform a feature selection of the relevant outputs and inputs. Regarding this heterogeneity, imagine here this data set. I will select the pointer. Imagine here this data set. in benchmarking, the usual is to compare all the firms against the other. So that way, the average efficiency that we can obtain is 0.88 and using all the three outputs. However, if we are intelligent and say, okay, here we can see three clear clusters, the red ones, the green ones, and the blue ones. So we can separate in these three clusters. And instead of using the three outputs, we select two outputs for each of the cluster, we can obtain even a higher efficiency. So this is something that because the cluster and the feature selection is important. So now moving to data envelopment analysis, the modelization of our problem. What is data envelopment analysis? Well, data envelopment analysis is a classical tool that it is used in benchmarking, and it is based on mathematical optimization. Particularly, DEA measures the performance through an score, which is this one. It is an average, a weight average of the outputs and a weight average of the inputs, where, as I have said, X are the inputs, Y are the outputs, and beta and alpha are the different weights for these averages. In such a way that those firms whose quotient, whose efficiency score is equal to 1 are said to be the efficient ones. So something about DEA, as you have seen in the previous formulation, can deal with multiple performance measures, both inputs and outputs in a single integrated model. And it also identifies a baseline for comparisons in continuous improvement program, and provides a specific target for improvement. Let's say when we compare, we can say, okay, you have to reduce this number of inputs in order to produce this quantity of output if you want to be efficient compared to this other one. So this is the formulation for the data envelopment analysis because, well, the efficiency is calculated as that quotient, but we have to solve the values of the betas and the alphas, and it is solved like that. However, this formulation uses all the outputs and all the inputs, and we don't want so because we want to obtain interpretability and so. So we can perform feature selection. Here you can see an example in which we move from O equal to 1 output until O equal to 10 outputs. And something that we can see in this picture is that, well, as we know, the DEA problem maximizes the individual and also the joint efficiencies as the number of outputs in the dataset increases. Here is something that we can see in the POC flows. Also, in practice, we can have so many outputs and inputs and few frames, so we can obtain something like overfitting and so on. And as usual in the real world dataset, the cost of obtaining the different inputs and outputs can be expensive, and some of them can be redundant and can explain more or less the same. And finally, the interpretation, and as I have said before, can be difficult if we use many inputs and outputs. So in order to reduce this number of inputs and outputs, we propose in this published paper with the author that I mentioned before, this new formulation of the DEA in which we reduce number of features. We have here this constraint. We said that the number of outputs to select is equal to P. It can be also modeled the number of inputs, the number of output and inputs at the same time, and so on. So now I have explained how we can perform the feature selection, but now we have to move to the cluster section. So first, I am going to show you which is the formulation that we propose to perform simultaneously the clustering and the feature selection. So the idea for this formulation is that we want to perform at the same time feature selection and clustering the DMUs in the firms. Also, regarding the clustering, we want to separate all the firms into 2 or more groups. and performing the feature selection technique in the inputs or in the outputs inside the cluster. And something relevant for this clustering and feature selection is that the selected inputs and outputs have to be the same within the cluster, but might differ by cluster. So the formulation that we obtain is something like this, in which we impose the number of outputs, in this case, to be lower or equal than PR. Since we try to maximize this objective function, this constraint will tend to be equal, not less, but exactly equal. So here we model the number of outputs, and here with these variables, these binary variables gamma, we select if each firm goes to one cluster or to other. So here we have the constraints in which we say for every cluster from 1 to C, we want everything to be exactly just in one cluster. Something that we can see here in this formulation is that we have the big M's M1 and M2. And well, we have some discussions about the values of the M2 and the F1 in order to impose some higher values for the value, because if we impose lower values for these big M's, we can like avoid a good solution. And if we use very large values of these various M's, we can obtain some numerical results. So we want to obtain good solutions, but without numerical errors. Here the same discussion for N1, so we obtain some upper bounds for these values. And now regarding constructive heuristics, because the problem before can be sometimes difficult to solve, we can have the constructive heuristic based on primal similarity, on dual similarity, and similarity in the efficiency level. To see it better, here we have some pictures. So imagine that this axis is one output, and this another axis is another output. So we can see more or less here one cluster and here one cluster, the red one and the blue ones. So if we don't perform any feature selection, the average efficiency will be less than 1. But if we try to put the red in one cluster and the blue in one cluster, we can obtain a higher efficiency. The dual similarity, it doesn't work like the previous before, in which the cluster were formed just by distance, but here we have to solve first the DEM model, and then once we have solved it, we are going to perform the cluster, but now based on the values beta and alpha, the different weights that we have obtained, no, on the original values of the outputs and the inputs. And another one, the efficiency similarity. Here we have also to perform DEA, and then we have to obtain the different efficiencies. So here we can see how the different efficiencies are equal to 1 for these 3 and equal to 0.5 for these 3. But if we separate in this cluster in red and this cluster in blue, we can obtain all these 3 DMUs to have an efficiency equal to 1, and all these in blue also to have an efficiency equal to 1, just separating by clusters. And the heuristic for the similarity in the efficiencies can be modeled. It is not just performing a k-means or that, but here we can model it. For that, we have to impose the lowest efficiency that we want to obtain, and the model will select the k more relevant, so it will separate between the efficient and the not efficient. And when we perform this selection, we only can build two clusters, the selected and the not selected. So if we want to obtain 3 or more clusters, it's just a repeated procedure. We have to select first between the more efficient and the less efficient. Then in the group of the less efficient, we have to separate again between the more efficient ones and the less efficient, and repeat on the number of clusters that we want. And after that, we can go to the local search heuristic in the case that the other one, the constructive heuristics, doesn't work properly. So in the local search heuristic, what we do is, once we have found the different clusters, we try to move one DMU from one cluster to one of to the other cluster, making both a swap or just a single movement. So we can try to improve the results that we obtain by changing the different friends of clusters. And now going to the numerical results. These are the requirements of the system in which I have run the different experiments. First, I use a simulated data set in which I use k equal to 150 firms. I have used 3 outputs, so it is easy to represent them in a 3D picture. I have used y equal to 1, only one input. And also I have to say that this input is the same for everything. So we have just to focus on the values of the outputs. And also, as you can see in the picture, data has been built. So using 3 different clusters, maybe you can see in these different lines, the 3 different clusters of 50 DMUs each and 2 outputs in each cluster. Let's say in this picture, we have only to use output 2 and output 3. For this cluster, we have only to use output 3 and output 1, and so on. So as I have said, using 3 classes, and 2 outputs, we can make every firm to be efficient, and all the contents M1 and M2 has been equal to 10 of the power of 5. So these are the different results that we obtain. These are the results for 2 clusters and pay the number of outputs from 1 to 3. As we can see, if we use 2 clusters and 3 outputs, we can obtain a really high result. These are the clusters that had been formed when using C equal to 2 and P equal to 3. Also, for 3 clusters using our original approach and moving from P equal to 1 to 3, when we use the P equal to 2, we can obtain the 1 also. Here, it has not been possible. And also using P to 3, we can obtain the 1. Also, it cannot be possible here because some numerical problems and the time limit and so on. But here we can see the picture when we use C equal to 3 and P equal to 2. So we can see more or less here this cluster, but there are some points in black that should be in green. Here, all the blacks, so it is a correct cluster, and here in red, so it is a correct cluster. So just swapping or moving these black points into the green, we can obtain an average efficiency equal to 1. Also, I have run here C equal to 3 using the k-means. In P equal to 1, it is true that we obtain higher efficiency than with our original approach and with C equal to 2, which is expected. But also maybe in P equal to 2 and 3, we may obtain the 1, but here we have a stop at 0.9 and 0.98. Maybe using the approach of the local search, we can go until the 1. And now, finally, without using cluster, we can see that the higher efficiency that we can obtain is 0.8. Now moving to the
Sandra,
real world data. Yeah.
1 minute. Okay.
Okay, so I'm going to the conclusions. So looking at the real world data set, it's more or less the same. So as a conclusion, we have developed a model that combines feature selection and cluster as a mixed integer linear programming problem. We have investigated a simulated data set and a real one. And also we have gained an interesting insight relative to the effectiveness of allowing more cluster or more features. Also, we have suggested several heuristics that one can use. And finally, some future lines of research are the interpretability of the clusters, combine our approach with interpretability constraints, and start this approach for outliers detection. And yes, that's all. Sorry for the time, and thank you so much.
Thank you, Sandra. You were on time finally. So I recall the audience that we will place all the questions to any of the speakers at the end, right? Okay, so thank you, Sandra. Our next speaker is Donato Maragno, a PhD student from the University of Amsterdam in the Netherlands, and he's going to talk us about mixed integer optimization with constraint learning. All yours, Donato.
Thank you, Christina, for introducing me. Do you hear me well?
Yes.
Yeah, great. So yeah, thank you, Christina, and thank you also, Senia and Sinia, Dolores and Emilio for making this seminar possible. Today I'm going to talk about mixed integer optimization with constraint learning, which is a joint project with some people from MIT and my supervisors at the University of Amsterdam. Okay, yeah. So before I go into constraint learning, first of all, I would like to mention briefly what mixed integer optimization is, even if I assume that most of you know what it is. So it's actually a tool, a powerful tool to optimize a given objective function subject to some constraints. And one of the most known optimization problems is the traveling salesman problem, where we have to find the route for a set of cities, to visit a set of cities, such that we visit each city once and we go back to the original point. So this is an optimization problem, and it is used so many times in real life for solving many different problems. Sometimes, though, there are real life optimization problems where functions, or either objective function or constraints, are not explicit, which means that we don't have a function for it and we don't know how to describe it in a realistic way. But when data is available, we can make use of it. We can learn using machine learning models the constraint or the objective function and try to embed it into the optimization model. Now, from now on in the presentation, I'm going to just talk about constraint learning, but it actually extends to the objective function as well. All right, let me give you immediately an example, and this is an example in the WFP, in the World Food Program setting. What we have here is an optimization model where the decision variable is a food basket. So we want to optimize the food basket subject to some constraints, like the nutrient requirement constraints, and then we minimize a procurement cost objective function. Now we know how to define the objective function, we know how to define the nutrient requirement constraints, but we have an extra constraint, which is about the palatability of the food basket. And the palatability depends on many different factors, like the culture or people, simply the people taste. And by palatability, I mean how well people know how to cook it and how much they enjoy the food. And so the palatability is a function of the food basket, X, and then I say that my palatability has to be greater than a threshold T. Now, this function, the palatability function, it's something that we can learn whenever we have data about how people like the different types of food baskets. So what we can do is we can use constraint learning. The idea here is that we have some decision variables X, some contextual variables W, for example, the country where people come from. And then we have y, which is the predicted outcome or outcomes if we have more than one. And using the previous example, which is actually a running example, I'm going to use it for the rest of the slides. Y is the palatability that we want to learn. Now, as you can see, that's my conceptual model. I have to minimize a function, which might be a function of a y, but also x and w. Then I have some constraints, and then my y, the predicted outcome, is learned using a dataset D. And the machine learning model that can be used is, it's actually one of many different machine learning models that can be represented using linear functions, and sometimes we need binary variables. But I will show you later how to do it in more details. Constraint learning, it's a really hot topic nowadays. There are many papers that make use of it. Here we wrote together with Dick Denertog and Adifa Jemisin a survey about optimization with constraint learning. And in this table here we can see so many different papers that use constraint learning, and the way they learn constraints might be in different ways. So in the columns you have different machine learning models like neural networks or ensembles of trees. And among these papers, there is also the one I'm going to talk about today, where we actually we present how to embed all the most known machine learning models. Okay, the framework that we present in the paper is the following one. We have the conceptual model, and the conceptual model is actually what we know how to define. So we have decision variables, we have contextual variables, some parameters, and then we have all the known constraints and objective function. And then, of course, we need an idea of what has to be learned. For example, we know that a palatability must be learned at some point, but we don't know what is actually the function defining the palatability. So in this case, we have some data for the palatability. We pre-process the data, and then the next step is to learn some constraints, the constraints for the palatability. The nice part here is that there is no model's dominance assumption, which means that the machine learning model that will be used to learn the constraint is not fixed a priori, but it's something that we can decide based on the performance of the machine learning model. Then something else is the trust region, and this is something crucial for the optimization, but I will show you later where it comes into play. And then we combine the conceptual model with the learned constraints and with the trust region to optimize a final optimization model. Okay, here there's a list of machine learning models that we can represent using linear functions and binary variables. So we have linear logistic regression, but also more complicated one like neural networks with a real activation function. And yeah, to be redundant, what we have here is, again, our conceptual model with functions that we know how to define. And then we have another constraint like the palatability that we want to learn. And the palatability is, for example, learned using a linear regression. And so what happens is that we fit our machine learning model, our linear regression. We get the vector beta and beta 0. And we use this function here to describe my outcome, learned outcome y. And then we can say that y has to be greater than a threshold. Now, that's actually the simple case of a linear regression. When we talk about decision tree, it's actually pretty similar. Now, imagine that this decision tree is a binary problem. It's a binary model. So using the same example, the palatability now, it's a food basket is either palatable or not. So we train our machine learning model, our decision tree, and that's what we get. So this is the trained model. We have 4 leaves, and only 2, the blue ones, are palatable, which means my X, if is able to reach one of the blue leaves, then it's predicted as palatable. Otherwise, it will be not palatable. So how can I force the palatability into the optimization model? One way to do it is forcing the X to reach this leaf. And this is done including these constraints into the optimization. Because if I use this constraint to reach P3, my leaf P3, it means that my X decision variable can go only in this path. and then it means that it's palatable because we are able to reach this length. On the other end, I can get a palatable food basket also reaching length P6, and this is this other set of constraints. Now, of course, one possible way to get a solution is to solve two different linear problems, the one including P3, the one including P6, and then the optimal solution will be the best one among the two, between the two. Or when the tree is really deep, or we use an ensemble of trees, what we can do actually is to use binary variables. So we can solve just one optimization model where we describe each feasible leaf using binary variables. Another machine learning model that can be represented using linear functions and binary variables is a neural network with a real activation function, and the real activation function is the one that you see here. So for this node, for the blue one, the output will be the max between 0 and a linear combination of the output of the previous layer. So as you can see, is a piecewise linear function, this neural network with the real activation function. And the way we can describe it is using this set of 5 constraints plus a binary variable z, which is one way to do it. This is not really efficient because we use some big M formulation, but there are some other approaches in the literature, like the one proposed by Anderson et al., where they use an iterative cut generation procedure to get the same solution, of course, but in a much faster way. Okay, now going to the next topic, which is about the trust region. We have this, imagine that we have this data set here. So each food basket is one of these dots. And for simplicity, we only have 2 different foods that define my food basket. And we have meat and oil. And each one is labeled as palatable or not. So that's an ideal case where we can actually train a machine learning model like a decision tree and get a training performance equal to 1, so the best score. And my feasible space is described by these 2 constraints. The oil has to be less than 15 and the meat has to be greater than 100. Okay, so that's what my tree is telling me. So if I use these constraints into the optimization model, and then I have also another constraint like the green line here, like a nutrient requirement constraint, so something that I know how to define. And then we minimize the objective function, which points in this direction, of course, because we want to minimize the amount of food to minimize the cost of the food basket. What we get is, as optimal solution, the star that you see here. But is it really palatable? Can we actually claim that it's palatable? I mean, according to the decision tree, we are in the palatable leaf. But it's actually really far from what we have seen in the trainings phase, right? So where the data is distributed. So a better approach that we propose is to use some trust region constraints. And basically these constraints are describing a convex hull around my data set. We don't need to find the convex hull, which is something extremely expensive in terms of complexity and time, but we can describe a feasible solution as a convex combination of points. And this is done by using this set of linear constraints, which is extremely fast in practice. And so here what we have is that a feasible solution to be feasible has to respect my the constraints coming from the tree, my nutrient requirement constraint, and also my trust region constraint. So the optimal solution now is, again, palatable according to the tree, is also much closer to what we have seen in the dataset. So I can have much more trust in the machine learning model. This formulation that you see here on the right, again, is extremely fast. But when the number of data points is huge, so we talk about millions of data points, it might be slow. It's actually slow because the number of lambda that we have here, and lambda is a variable now, is equal to the number of data points, big N, capital N. So it means that if my data points has 1 million data, when my data set has 1 million data points, I also have 1 million variables in the optimization model. So what we propose is to use a column selection algorithm, and the column selection algorithm works such that I start from a subset of points, and then I find the convex hull of these points, like the red ones here in the picture, here. And then iteratively, I look for a new point in my dataset to enlarge the convex hull. And then I will stop when my optimal solution, the black star here, is included in the convex hull, in the red convex hull, which is not exactly the convex hull of my full dataset. It's just part of it, but it's the part that I care about. So this actually improves a lot the computation time, and we are also something like 10 times faster. Something else that I forgot to mention it's about clustering, and this is actually when we have data that is spread. There is not actually a uniform distribution of data, but I have some clusters, which means that there are low density regions in the convex hull. And the question is, again, do we trust the predictive model in this empty region here? So what we suggest is to use first clustering, and then for each cluster we define a convex hull. And we force the optimal solution to be in one of these convex hulls. That's the idea. Everything I talked about so far has been developed in Python. So at this link, you can find a package where you can use constraint learning. You can use optical, which stands for optimization with constraint learning, to train the constraints or the objective function. You can learn one or more constraints. You can learn constraints and objective function using some data, and then optical will take care of embedding these constraints into the optimization. So it's a pretty nice way to learn constraints. Everything is based on scikit-learn for the learning part, and Pyoma is for the optimization part, for modeling the optimization model. There is also a demo available, but yeah, for this one, actually, I mean, I will need other 10 minutes, so probably there is no time. But if you are curious, you can just have a look at the GitHub repository, you will find it there. So this was my presentation. I think, yeah, if you have questions, probably at the end of the next talk.
Yes. Thank you, Donato, for your nice presentation. We will go now for our last speaker, Yurii Malitskyi. He's an assistant professor in applied mathematics from Linköping University in Sweden, and he will talk to us about adaptive gradient descent without descent. The floor is yours, Yurii.
Thank you very much. Thanks a lot, organizers, for inviting me here. Hope I will manage to be in time, but if not, just interrupt me if I miss the deadline. Yeah, indeed. I will talk about a recent paper, adaptive gradient descent without descent. It's a recent paper with Konstantin. You can see the link there if you're interested to find out more details. So in the talk, we will study the basic optimization problem. We have some nice convex and differentiable function f, and we want to minimize it. It's unconstrained problem. And since it's such a basic problem, of course, there are plenty of methods how we can solve it. For example, yeah. So there is gradient descent, and many extensions of gradient descent, like accelerated gradient descent, Newton method, the method when we assume third availability of third order oracle. We can go back and assume less, for example, by considering stochastic methods or coordinate. Important here is that gradient descent is like a backbone of all these methods. So if we can understand well gradient descent, maybe we can do also something nice with other methods. The gradient descent is an old method. It goes 19th century to Cauchy. There are many major papers on the way, and throughout the talk we will use extensively the following definition. We will call function f L smooth is equivalent. Sometimes we will call that gradient is a Lipschitz when this inequality holds for all x and y, of course, of all space. So it means that we have some control over gradient changes. It cannot change too fast, right? If our function f is 2 times differentiable, it's the same as to say that Hessian is bounded by constant L. The norm of the Hessian is bounded by L. Okay, so the basic classical result is as follows. So if our function is convex and L smooth, we use a step size alpha. Alpha is this constant alpha is a step size. So if alpha is small enough, in particular if it's less than 2 over L, we can prove convergence to a minimizer. If we pick step size like 1 over L, we can quantize the rate exactly. So in particular for our energy for function values, x star is our solution. We have 1 over k rate. It's not important this complicated expression. For us, it's just important that it's 1 over k. Maybe it's good to remember that in the nominator we have this constant L. So probably it would be better for me to write L over k, to include both. So that's a basic result. Okay, so method is very simple to implement, but if we there is one thing. So assume that we have some convex function which we want to minimize, and our argument x they live on a plane. Our function is like and the function values live in the zeta space, as a third dimension. So we can construct the level sets of our function f. Since it's convex, it may look something like that. So we are at the point blue. We are in the blue point. We want to find the red star, the solution. And if we are going to so we are going to run gradient descent. If we pick small enough step size, then yeah, indeed we converge to the point, to this one. If on the other hand, if we pick it very small, then probably this convergence will take many more iterations. Because of that, it will be more expensive, of course. On the other hand, if we use larger step size, we might just diverge. So we just go into this region and we'll jump from one region to another and go to infinity like that. That's why that picking this step size is not trivial. In other way, although the method is very simple, we still need to know how to find the step size alpha. It's not free lunch. And so what we're going to do? On the other hand, as I said, it's a really old method. So apparently there are already a lot of existing approaches to for this issue. So one, the most like general probably, is to use line search. Line search is another for loop you have to run in every iteration. In particular, in every iteration, k, start with some step size, with some guess, whatever, it's not important. And we compute xk plus 1, next iteration, compute it, and we check whether this inequality holds for some constant c. It's not important. If this inequality holds, meaning that we have some decrease in our energy, our f decrease, then we break this for loop and say, okay, the step size we tried was good, and we go to the next iteration. If this iteration doesn't hold, go back, decrease step size alpha, and do the same. So eventually, if our function f satisfies the assumption we talk about, then eventually f must the step size must satisfy this inequality in the end, and so it will always break this for loop. That's pretty reliable procedure, and if you have no idea which step size to use, probably it's a good thing to do. On the other hand, it's clear that this procedure is more expensive than gradient descent. In particular, yeah, like in every iteration, we need not one evaluation of gradient, but probably many more. We don't know, and actually we don't even know how many. We cannot say about the complexity how many iterations of the gradient we will need in the end. Another approaches, very good one is to use Pollack step size. This is a version of gradient descent in the following form. So you pick step size alpha k, strange equation. F star is our optimal value, and you use it. This method is quite good, but unfortunately, it requires us to know the optimal value. In only a few problems that are interested in practice where we indeed know F star. In general, this constant is not available to us. So that's why it's not very practical. But if you know F star, it's really a good idea to try the Pollack step size. Finally, there is a popular Barzilai-Bourgain step size, which goes as follows. It's quite complicated formula, but no, I mean, you just take current gradient, previous one, and do some expression and use it in the update. So this step size was proposed for quadratic problems. Unfortunately, actually the theory only works for quadratic case, and you can construct a nice convex function, like even strongly convex, where this method will fail, or even like modification of this method will fail. So it's not reliable. So that's like few most important options with which you can handle the issue of the step size. But it's as we discussed, all of them have their drawbacks. So now we will describe what we proposed. Again, we recall that we will assume that function f is L smooth. Our method is a simple modification of gradient descent where we pick step size adaptively. So if you don't know, you just want like to invent some heuristic and you don't know constant L, probably, and you know that the step size must be proportional to this constant L, kind of like it will be good if it's proportional. So, a naive idea is to try this gradient descent where you define step size like a proportional to 1 over L, where L is your local constant of your local Lipschitz constant. It's a ratio between different gradients and values. That's a very naive idea. And actually, if you have some concrete problem, you may try and it will work. So it's pretty, actually it makes sense. Fortunately, it's also not that hard to find these counterexamples. That's why we proposed a new method, which will work reliably. But as you see, it's not that different from this naive approach. It's a bit more complicated, the update, but on the other hand, not much. So the main difference is the step size. On the one hand, it's also 1 over 2L. But on the other hand, we control how quickly alpha k can change from one iteration to another, how fast it can grow. Can grow, right? Because the square root is bigger than 1. So alpha k can be bigger than alpha k minus 1. But we must define how much it can be big in how much time. And theta is just the ratio between step sizes. That's not important. So it's important that on one hand, alpha k is approximation of local Lipschitzness, and another, we control how quickly it changes. So we will consider in more details in the next slide. And the iteration k, we assume that we have xk and we have our gradient and theta k minus 1. So what we are going to do? We compute our gradient at a point xk, reuse the previous already computed gradient at point xk minus 1, and with this we compute constant lk, it's like a local Lipschitzness. And then with this information, we proceed to compute alpha k. So alpha k is just a simple substitution that doesn't require any expensive things to do. And after we compute alpha k, we go and update our iterates xk. We compute xk plus 1. And after that, we update some simple parameters like theta k. Basically, in terms of computation, it's the same as gradient descent. You just need to compute one gradient per iteration. You don't need anything else, no values of f. And on the other hand, gives you some way to adaptively pick step size alpha k. In particular, we can, I wrote it in 3 lines now. Instead of writing lk, I substituted this long expression into alpha k. So you may wonder why we have such strange conditions, at least the square root and this one. So I cannot explain it really well without showing the proof, but the main idea is that how the proof of all this optimization method works. In most cases, you construct some discrete Lyapunov energy, like the same you do in with solving differential equations. You construct some Lyapunov energy and show that it increases along iterates. So here you do the same. You construct some energy and you show that along iterates of your method, this energy doesn't increase, or it either stays the same or decreases. So in this case, we construct some strange energy, ck plus 1, quite different from common in optimization area. What we want to do, we want to show this inequality. Unfortunately, if we just write ck plus 1 and ck, it will be some nonsense. It's difficult to compare them. So there will be some extra terms that we have to kill. These extra terms will be exactly those that appear in the algorithm. So the first term denoted in red is like that, and if you see it's actually y step size alpha k has to be smaller than this number, just to make this red part negative. And similar, you want to do this with similarly you want to do it for the second term. It's a green one. Yes, you want to make it, because fx k minus 1 minus fx star is always positive. You want to make green term negative. And this is, I mean, it's not immediately clear, but if you just like write in 2 lines, you immediately obtain the same inequality, that alpha k has to be less than the square root and multiply by alpha k minus 1. So that's just intuition why how we came up with such strange update, kind of natural. So what we can prove, if we assume that f is convex and not globally Lipschitz as we assumed before, we assume only locally Lipschitz gradient f, which is much more general. For example, functions like xp, exponential, tangents, they do not satisfy property of to have global Lipschitz gradient, but for us it's fine. Like all of these functions are locally Lipschitz. So we consider a more general class of functions. So that's enough for our purposes. So if we assume this, we can prove, as before, convergence to a solution, and moreover, we will have the following rate. For some xk ergodic sequence, we will have some constant divided over sum of step size, and we can show that it's also 1 over k rate in the worst case. But since we have some concrete alpha I step size, and alpha other step size were chosen in an adaptive way, so practical point of view, we may hope that this alpha I are much larger than the global estimate that the global constant of global Lipschitz constant provided us. So in practice, it may be much better. Practice. Why we have 1 over k? Because if, for example, if you assume, just for simplicity, we don't need, but for simplicity, if you assume that gradient is a Lipschitz, We can prove that all our step size are actually bounded by this constant 1/2L. And because we have sum of the step size, we obtain k in the denominator. That's how we get 1/k in the worst case. Okay, let's quickly see how it works. For example, this is like some typical logistic regression, typical problem with one of the popular data sets. Compare gradient descent. We compare Nestor method that probably works faster than gradient descent. Its rate is 1/k squared. And so we compare these two classical methods with ours. Both three methods use the same number, use just one gradient per iteration. And as you see, in our method, although our method has rate 1/k, it's still much faster in practice. There are many more experiments in the paper. I will not go into this, and basically I have to finish right now. So yeah, I just quickly go. There are some extensions. I will go into this. So there are some open questions if you're interested in. Because if you have something, if you prove something for extension of gradient descent, now it's tempting to do the same for other variants of gradient descent. So that's what open questions are about. Okay, thanks a lot. If you have questions, you can ask it later.
Thank you, Yurii, for the excellent presentation. Yeah, so as I realized, your method is more efficient and faster than the others. It was very impressed. So, but now, yeah, we want to open the floor for the questions to all the speakers. So, if you want to ask the question, then you can raise the hand, and we will give you rights to talk, or you can use the chat. So yeah, there's okay, there's a question from Ilker. Or it was a misclick, I don't know.
I'm sorry, it was a misclick.
Okay. Okay, great. Okay, we have a question from Nagisa. So let's give, yeah. Go ahead, please.
Thanks. Can you hear me now?
Yes, yes,
Thank
excellent.
you. Thank you for the presentation. I have a question for the very last presentation given by Yurii. I hope I pronounce correctly.
Yeah, great.
I was thinking like it's like a really kind of strong method, and like the idea was very fascinating. And I was thinking, do you think it's easy to extend to the case where we don't have an exact gradient or like function value? Like, let's say stochastic gradient descent doesn't use like a exact one. Then
exactly. So in my slide, I show some experiments with stochastic gradient descent. Unfortunately, and we did many experiments in the paper. Unfortunately, we presented as a heuristic. We couldn't prove anything for this method, but still, surprisingly, we applied it even for non-convex, like some deep learning, training deep learning, and it worked pretty well. And what is interesting, it gave us really large step size. My just at some state-of-the-art SGD, and despite that, we still like showed even better results. So we don't understand this phenomena, and not it's not the same across all the data sets, but very often we observe this.
I see. And so so you try to kind of analyze the stochastic version that's available. Like it was not really easy. Like analysis.
We even have some proof, but like that theorem is not interested. It's like it doesn't provide any benefits. It's just like it's possible to prove in the convex case. In practice, it might work. It's just like we don't know how to analyze in theory this like is a better way.
Thank you for the answering.
Yeah, thanks a lot.
Any other questions? Oh, may I ask Donato about So you told something about long trees, but as I understood, long trees, it's not what you want to have, and also you can have not only one feature in the node, so you can have, let's say, oblique cuts in your nodes. Is it correct, or?
Sorry, you can have what? I missed the connection. You can have.
Oh, sorry. So, is your does your decision trees have oblique cuts, or it's only
yeah.
one feature in the node?
Yeah, actually, it's not important. We can have also oblique cuts, so we can have multiple features involved in each cut, each split. So that's not a problem. And what we actually see that is when we have oblique cuts, then we can get similar performances with a shallow tree instead of a deep tree. And having a deep tree is actually not something that we dislike. It might be a problem for the optimization though, because then we have to introduce binary variables. And if the problem is itself a linear programming problem, then usually we don't have binary variables. But when the tree is deep, then we need to introduce them. Otherwise, the number of optimization problems that we have to solve is equal to the number of, let's say, positive leaves or number of leaves that we actually are caring about.
Thank you. And I know that the classes you have in each leaf, it's not the same classes as in, let's say, usual machine learning task. But what I don't know, is there a need to have, for example, more classes than only two, or it's more like to split to make a functional form? So you need.
You mean classes in the prediction problem?
Yeah.
So now the package that we developed is just for binary classification, but the theory that we present in the paper is for both actually. So we can also use multi-class classification. Itself, the formulation is it's nothing special. It's pretty the same. So I will say that when we actually deal with real problem, then we have to see how it performs. And not only from a prediction point of view, so not only in terms of accuracy, but also when we embed it into the optimization, because what we see is that optimizing is actually, most of the time, we are looking for points, feasible solutions that are trying to fool the machine learning model. Because if you think about the case study that I presented, we have the palatability that somehow goes in an opposite direction compared to the objective function. So the objective function is pushing the optimization in a certain point that the predictive model is not performing well. And so we have a misclassification or a misprediction. That's why we introduced the trust region idea. So now to go back to the question, I will say that binary or multi-class classification depends on the problem. We can make a multi-class problem binary, but sometimes when multi-class performs better, then we can keep it. And yeah, there's a similar formulation for it.
I see. Okay, and just a small question, the last one from my side. So I didn't get it from the formulation, but are you doing this machine learning of the constraints and the optimization simultaneously, or you have two steps?
It's actually two steps. So the first step is two big steps. So the first step is we train the machine learning models. We train different models. At least this is actually how optical works. But you can choose. You can train these machine learning models. You see the performance. You choose the best one. And then afterwards, you can embed the constraints into the optimization model, and then you solve the optimization model. So the idea is that you don't know what's the function that you are learning. You don't know what's the structure of the function, but you're learning it. But again, you are learning the function, which means that you're learning fitting some parameters during the training, but those parameters are fixed when you go to the optimization. So it's actually a two steps. Yeah, you're right.
Yeah, so it's your data actually, yeah, to the optimization model. Thank you very much for this clarification. Thank you. So if any other questions, we are you have time to ask. I don't know, it seems to me there's no questions. So I don't know, yeah, we can close the session then and say great thanks to all of our speakers. It was very interesting and it was from very different, not very different, but yes, a little bit different areas. So a lot of food for our minds from today's seminar. So thank you very much. And see you next Monday. It's going to be a usual seminar series with one speaker. So, but thank you very much for participating in this excellent event. Yeah.
Thanks a lot for inviting us.
Thank you.
Thank you.
Thank you.
Thank you very much,
Thank
everybody.
you.
Thank you.
Thanks a lot.